Good afternoon, dear participants of the 4th International ProfIT Conference. Let me introduce myself. My name is Yurii Skob. I am a presenting author of the report on the topic, Mathematical Modeling of Pressure Effects from Hydrogen Explosion, on behalf of a team of the authors from Ukraine, Zhukovsky National Aerospace University in Kharkiv, Glushkov Institute of Cybernetics, and Taras Shevchenko National University in Kiev. The aim of the work is using the means of the mathematical modeling to make an analysis of hydrogen mass concentration and pressure fields in the area of accidentally released and exploded gaseous hydrogen at a refueling station. Physical processes of hydrogen release, hydrogen-air mixture formation, spreading, and subsequent explosion in the surface layer of the atmosphere can be considered as an object of the research. The subject of the study is a mathematical model of physical processes of multi-component gas mixture movement and explosion with generation of shock pressure waves, which caused negative influence on environment. An explicit time-dependent finite difference first-order approximation Godunov method is used as a research method to solve the stated scientific problem. The relevance of the study is determined by the need of the community of experts in the field of safety assessment of high-risk industrial enterprises in reliable and effective mathematical models that will allow simulating complex physical processes that arise during an accidental release of such explosive gases as hydrogen into the atmosphere. Such models should replace expensive large-scale physical experiments for analyzing and predicting the consequences of an accidental explosion for the environment. The instant release of given amount of gaseous hydrogen is considered. The admixture forms a gas-air cloud with the air, which moves under the influence of the wind and gradually dissipates in the surface layer of the atmosphere. The system of differential equations of motion of a three-component gas mixture includes the laws of conservation of mass, momentum, and energy of the mixture, supplemented by the laws of conservation of hydrogen and combustion products mass. The equation of state of the mixture completes the system of equations. According to the suggested combustion model, it is assumed that the global instantaneous chemical reaction takes place in the volume where the concentration of the admixture is in the inflammability range. It means that the values of the parameters of the gas mixture in the control volume are instantly changed by the values of the corresponding parameters of combustion materials and remnants of the one of the mixture components, combustible gas in the case of thin mixture or air in the case of rich mixture. It is assumed that the flame front propagates with infinitely large speed. The developed mathematical model of gas release and explosion in the atmosphere was validated using data from physical experiments and other models' simulation results. Firstly, an explosion of the hemispheric homogeneous stoichiometric hydrogen-air mixture cloud was modeled experiments at Fraunhofer ICT laboratory under the ambient conditions. The pressure development at the distances of 35 meters, the point B on the figures, and 80 meters, the point C, from the epicenter of the explosion, the point A, was examined during the computation. The model over pressure history in control points B and C is shown on figures A and B and compared with a large-scale physical experiment and results of other models. An explosion of stoichiometric propane air mixture was also carried out. Look at the figure C. The computational results show acceptable accuracy and allow to consider developed mathematical model as an adequate instrument to simulate gas explosions. Using the developed mathematical model, an accidental explosion at the hydrogen dispensing refueling station was considered. Two potential locations of the station were set, points A and B. They differed by the distance from an epicenter of the explosion and surrounding infrastructure buildings. In order to assess the shock pressure wave loads on the environment, the overpressure history at control point C near one of the buildings was collected, and non-stationary pressure and hydrogen concentration fields throughout the industrial territory were analyzed. Installing a protective device around a potential compressed hydrogen release site significantly changes the hydrogen concentration field before the explosion. The presence of an obstacle in the path of the blast wave also restructures the maximum pressure field, which reduces the impact load on buildings. Variants of different heights for partially surrounding the explosion site with a protective structure were also considered to assess the possible consequences of the accident on the surrounding buildings. The most effective protective device was a solid wall in the immediate vicinity of the buildings. Finally, the following conclusions can be formulated as follows. The mathematical model of gas mixture explosion and dispersion of the combustion materials in the open atmosphere was developed. The model was validated against the data for physical experiments and other models simulations for hydrogen and propane explosions. Non-stationary fields of dangerous combustible admixture and combustion products concentration and pressure during explosion at hydrogen refueling station were obtained for different station locations. The spacious distribution of maximum overpressure was calculated, which can be used during the analysis of shock wave loads on humans and buildings near the accident epicenter under different protection conditions. Obtained information can be used by safety experts during certification process of high-risk industrial objects, which deals with such dangerous matters as hydrogen fuel. Thank you very much for your attention.